Okay, so let me begin by, so can we start then? I'll introduce Professor Munshi then, quickly. Somebody's
yes, sir. The session is live now.
Yeah, so Madam Khaduja's thing is, I think, on, and I can hear. Maybe she has to mute it. Yes, that's fine. Okay. So it gives me great pleasure to introduce Professor Ritabrata Munshi, who is known for his outstanding contributions to analytic aspects of number theory. When he has been recognized the world over for his contributions, in India with the Shanti Swarup Bhatnagar Prize, the Infosys Prize. He has given an invited talk in the International Congress for Mathematicians. He is known for his very deep work on the subconvexity bounds for a large class of L functions, which are considered breakthrough in the area. It gives me a tremendous pleasure in inviting Ritabrata Munshi to give this talk for the INSA.
Thank you, and thank you, Balaji, for the nice introduction. So I'll just start my sharing my screen. Hopefully it works.
Maybe make it full screen. Yeah, full screen. That's it. Oh, great. It works.
Okay, good. Okay, thanks.
I'll mute mine.
Okay. All right. So yeah, so I'm going to talk about L functions, actually just the analytic theory of L functions. And so I'll begin with the origin of L functions. So I'm going to really go back like more than 2000 years and start with Euclid. Okay, so this is where we start anyway in school. So the first thing that I want to say is Euclid proved that there are infinitely many primes, right? So his proof was by contradiction. So he supposed that there are finitely many primes. He just lists them down. And then P1, P2, Pn, and then to take the product of them and add 1 to it. This is an integer which should have a prime factor, but it cannot have a prime factor because if any of this prime factor divides this number, that prime factor has to divide 1 as well. So that was the contradiction. So there has to be infinitely many primes. So this is a fantastic proof, a very short proof of infinitude of primes. But the problem with this proof is that you cannot really generalize this to arbitrary sequences, right? So, so given any sequence of integers, positive integers, it's a standard problem in analytic in number theory actually to find out whether there are infinitely many primes or whether there are any prime in that sequence. Okay. For example, you can look at sequence in arithmetic progression. So here is one example. So you are looking at numbers of the form 10n plus 3. So it's the integers whose last digit is 3. And you can ask whether there are infinitely many primes of this form. And it turns out that it's quite difficult to generalize Euclid's proof to prove infinitude of primes of this form. Okay, you can even ask something deeper than this and much more difficult than this. So are there infinitely many primes of the form n squared plus 1? Okay, this is a very sparse sequence, and also, of course, Euclid's method fails, and also whatever we have developed in the last 2,400 years after Euclid fails. Okay, so nothing works for this. So no one knows whether there are infinitely many primes of the form a squared plus 1. Okay, so so there is the reason to find new proofs of infinitude of primes in sequences. And so after a couple of thousand years after Euclid, Euler came up with a new proof of infinitude of prime. So he introduced this series. Now we denote it by zeta s. So it's just the reciprocals of integers raised to the power s. And if you take s to be bigger than 1, then this series converges absolutely. Okay, and then Euler observed that the fundamental theorem of arithmetic, which says that every integer can be written uniquely as a product of prime numbers, is equivalent to saying that this zeta function has this nice product formula. So if you take s to be a positive, s to be a real number greater than 1, then zeta s can be written as this product. Okay, and now if you suppose that there are only finitely many primes, then this right-hand side of this product makes sense for s equals to 1 as well. Okay, But if you look at the series and take S nearly equal to 1, then this series diverges. Okay, so that's the contradiction. And so that again implies that there are infinitely many primes. So Euler gave a different proof of infinitude of primes. And the nice thing about Euler's proof is that you can use this in other scenarios. Okay, and that's what Dirichlet did. And this is the birth of L functions. So Dirichlet actually proved that any reasonable arithmetic progression will have infinitely many primes in them. Okay? Any reasonable means if you look at progressions like A plus B n, where A and B are fixed, if A and B are co-prime, then there are infinitely many n's for which A plus Bn is a prime. Okay, of course, if you take something like 2 plus 4n, you will never hit a prime because 2 will always divide that. So you have to take A and B to be co-prime. Okay, and so to prove this, Dirichlet introduced sort of a twist of the zeta that Euler introduced before him. So he took a, so if you suppose you were interested in finding primes in the sequence A plus NB. So B is a fixed positive integer, and A is greater than 0 and less than B, and A and B are co-prime. And you want to show that there are infinitely many primes of the form A plus NB. Okay, so then you take a character of this multiplicative group, okay, and define this L series. Okay. And again, Dirichlet observed that this also has, because of the same reason, it can be written as a product. And this product is called Euler product because Euler was the first person to analyze this thing. And then from this product, Dirichlet came up with this formula that if you are taking the reciprocals of prime raised to the power s, okay, and the prime is in the arithmetic progression that is congruent to A modulo B, so it is of the form A plus NB, then this sum is equal to this sum of logarithm of this function. Okay? And from here, so if you want to show that there are infinitely many primes of the form A plus NB, what you have to show is that when S equals to 1, the right-hand side is infinity. If the right-hand side is infinity, the left-hand side also has to be infinity, and that will mean that there are infinitely many primes. Okay, so why is the right-hand side? If you look at log of LS chi, okay, so there are only finitely many chi's. So if we prove that one of these guys is infinity and the other guys are just finite, we are done. Now, if you take chi to be the trivial character, then LS chi is the Riemann zeta function, that the zeta function that Euler was studying. And for that, we know that it already diverges at equals to 1. Okay, so there is it's slightly different from that because it will miss the primes dividing the modulus B, but that will not hamper the infinitude of the sequence. So for chi equals to the trivial character, this is infinite as equals to 1. Okay, so the log is also infinite. But what about the other characters? And Dirichlet showed that if you take a non-trivial character chi, then this L1 chi, so if you plug in s equals to 1, is neither 0 or infinity. Okay, it's neither 0 nor infinity. So that means log of LS chi or log of L1 chi is not infinity. Okay, and to prove this, he introduced what's called the class number. Okay, and from here, he proved that there are infinitely many primes of the form A plus NB. Okay. Okay, so with this proof, which was done in 1837, Dirichlet opened a new chapter in number theory and what we today call analytic number theory. Okay, okay, and the method he introduced is the following: that if you want to study a sequence, say AN, then you define the associated Dirichlet series, which is defined like this: AN by n to the power s. N is 1 to infinity. And if you want to show that that there are infinitely many ANs which are not 0, what you have to show is that this series is infinite at some value of s. So to understand the sequence, we have to go to the corresponding Dirichlet series. Okay, so it's called Dirichlet series because Dirichlet was the first person to use it in the context of number theory. Okay, so here is another problem which was of interest back in 19th century. So Gauss was looking at this prime counting function. So pi x is the number of primes less than x. And as a teenager, Gauss conjectured, which is now known as the prime number theorem, PNT, that then the count is asymptotically x by log x. Okay? So that means that the density of primes of size x is like 1 by log x. Okay? And then Riemann in around 1860 realized that one can do something about Gauss conjecture if one understands Euler's zeta function better. Okay? And he was the first person to look at the zeta function, and not for real s greater than 1. He started it as a complex function. So s he took as a complex variable, sigma plus ip. Okay? And then he proved a lot of things. And though in his short memoir, he didn't write down the proofs, but we now understand that he already had the proofs back then in 1859. That the first thing which is easy is that this zeta s converges for any in the half plane sigma greater than 1. Okay, and then he showed analytic continuation. That means that that zeta s makes sense for any value of s except s equals to 1, where it has a pole. Okay, so it has to go blow up at s equals to 1, but at any other point you can make sense of zeta s. For example, the zeta of 0, which is actually 1 plus 1 plus etc., will have to be like minus 1/2, and zeta of minus 1, which is the sum of the positive integers, will be like minus 1 by 12. Okay, so as Ramanujan also wrote this down in his notebook, but he used his own ideas, own methods, and not really using complex analysis. Anyway, so this is a picture of the complex plane. And what Dirichlet proved is that if you look at this part, this half plane over here, s greater than 1, sigma greater than 1, then, so then the zeta s is absolutely converging, and it gives you, and the Euler products also absolutely converges. And then it can be continued to the whole complex plane. It has only one pole at s equals to 1 over here. And he also proved that there is a functional equation, I will write it down later, that relates the value of the Riemann zeta function at s with its value at 1. So there is the 1/2 point is kind of the point of symmetry. So if you take a line going through 1/2 equally away from 1/2, then the value at 2 points are more or less equal up to a gamma factor. So that's the functional equation. And using that functional equation, Riemann came up with this remarkable formula where in one side, you'll see that we have the primes. So this runs over the primes. And on the other side, you have the zeros of the Riemann zeta function. Okay? So you have two explicit terms, x and log 2 pi. And the remaining terms, which are mysterious, are coming from the zeros. This corresponds to the zeros of the zeta function. Okay, and so from here, he realized that if you want to understand the number of primes, which is basically trying to understand the left-hand side, you have to understand the right-hand side, which is basically trying to understand the zeros of the zeta function. Okay, and he also realized that if you want to prove the prime number theorem, as conjectured by Gauss, it was enough to show that this zeta function, which now makes sense for all values, does not vanish at 1 plus it for any t real. Okay, so it's not vanishing at this line over here, passing through 1. Okay, so that's called the age of the critical strip. Okay. Okay, and he came up with this remarkable conjecture that actually the zeta function should not vanish up to the central line passing through 1/2. So in this half plane sigma greater than 1/2, there should not be any zero. This is the famous Riemann hypothesis. And if you have this Riemann hypothesis, then you will get a very strong approximation for the counting function for prime. So it will be like the integral 1 by log x plus an error term, which is like square root of the size root x. Okay, so it's a very strong approximation for pi x, but this is also equivalent to proving the Riemann hypothesis. Okay, so that's basically the history, the starting point, Euler, a contribution of Dirichlet and Riemann. And now let's try to summarize. So what we are looking at are functions in complex variable, which are given by some Dirichlet series and also given by an Euler product. So the first example that we are looking at is called Riemann-Jitter function, because Riemann actually took the major step ahead in analyzing this function. And yeah, so there is a region of absolute convergence, sigma greater than 1, when both the Euler product and the Dirichlet series converge absolutely. Okay, and there is an analytic continuation. This makes sense for all values of S with a simple pole at S equals to 1. And as I said, that there is a relation between the value of zeta at S and 1 minus S. You have to multiply with certain factors. So this is the, so if you look at the Euler product over here, this is running over all the finite prime. But as you know that there is a prime at infinity, and if you compute the Euler factor of the prime at infinity, that turns out to be this gamma factor over here. So if you multiply and so you complete the Riemann-Jitter function, then that is called psi S. Then the value of psi at S is same as the value of psi at 1 minus S. Okay, so that's the functional equation. So these are the properties. So it should have a Euler product, a Dirichlet series, analytic continuation, and functional equation. These 4 properties are basic things that you're looking for when you want to define an L function. Also, Dirichlet L function, which again, recall it corresponds to a character of the multiplicative group Z modulo V C star. Okay, this also has a Dirichlet series and Euler product, both converging absolutely in a half plane. And it also extends to the whole complex plane. Now, if chi is non-trivial, there are no poles. Okay. And again, it has a functional equation. Okay, so now you have to, the factor at infinity is slightly different. It also involves the conductor B. Okay, so B is the period of chi. And if you multiply LS chi, if you complete it up, then it is related to the value, not of the complete real function at 1 minus x, but the conjugate. So here is the L function corresponding to chi bar and not chi. And then also there is something called the root number, which is a sign. It's not exactly the same, but it's twisted by a sign. The sign involves what's called a Gauss sum. Okay, so these are the 2 examples of classical L functions, the Riemann-Jitter function and Dirichlet L function. And there's these are called degree 1 L functions, because if you look at the Euler product, you'll see that this is like 1 by a polynomial of linear polynomial of 1 by p to the power s. Okay, so each factor is linear in 1 by p to the power s, and so it's called degree 1. Okay. But you know, as we go along, you encounter higher degree L functions, and here is one source of higher degree L functions called modular forms. Okay, so let's start with a very concrete example of a modular form. It's called Ramanujan discriminant form. It was started by Ramanujan. So you take, so delta Z is given by this infinite product. Okay, so this Q is actually e to the power 2 pi I Z, and Z is restricted to the upper half plane. So H is, Z is x plus IY, where Y is greater than 0. It's on the upper half plane. Then you'll see that this product converges, so it makes sense. And if you expand the product and collect terms and write it as a series in Q, then these coefficients are called Ramanujan tau function. And Ramanujan wrote down some remarkable properties of these tau functions, and which later came to be known as the Ramanujan conjectures. One of them is that this tau function is multiplicative. So if m and n are 2 co-prime integers, tau of mn is tau m times tau n. And the more difficult conjecture was that the size of tau p is bounded by twice p to the power 11 by 2. And you may wonder where this number 11 by 2 is coming from. And that is because we have this delta z to be a modular form. Okay? So we tell, so delta z satisfies this transformation property. The delta at az plus b by cz plus d is cz plus d to the power 12 times delta z for every matrix A, B, C, D in SL2Z. It satisfies this transformation property with weight 12. Okay, and so this delta is actually a modular form of weight 12 for the group SL2Z. And is 11 here is the weight minus 1. It's 12 minus 1. Okay, so in general, Ramanujan's conjecture has been generalized to general modular forms where instead of 11 by 2 over here, you'll have p to the power the weight minus 1 by 2. All right. Okay, so yeah, so as I said, it's a modular form. Now you normalize because they are size 11 by 2, you divide by n to the power 11 by 2. These are the normalized Fourier coefficients of the discriminant form. And then Hecke defined this Dirichlet series corresponding to delta. So he took the normalized Fourier coefficient and divided by n to the power s. And he showed, and this is equivalent here, something much deeper than just fundamental theorem of arithmetic. It's actually equivalent to this multiplicativity over here. Okay, so that this has a Euler product. Okay, and I didn't write down what happens when m and n are not co-prime. Then it satisfies a recurrence formula of degree 2, and that's why here the Euler product is not of degree 1, but it's of degree 2. Okay, so this is an example of a degree 2 function. And again, Hecke actually showed that this extends to an entire function, and it satisfies a functional equation. And here again, you have to multiply with a suitable gamma factor, and the value of the computative function at s is related to 1 minus s. In fact, they are just equal. Okay, so now we have seen an example of degree 2, and you may ask whether they're degree D L functions for any D, and they're related to what are called automorphic representations, a special representation of Lie group. So if you take the Lie group GLD over the adults over the field of rational numbers and an automorphic representation of that, then corresponding to that automorphic representation, we can write down an L function, which is defined as a Euler product like this, where each Euler product here, as you can see, it's of degree D. So for each prime, what we have over here, there are D many factors. So it's a polynomial of degree E in 1 by p to the power s. And again, there is a factor at infinity, which is again a product of gamma factors. If we multiply the L with this gamma factor, this has a functional equation. So all this follows from the theory of automorphic forms. This was mainly done by Godema and Jacquet. And okay, so now once we have such a functional equation, so as you know that we are mainly interested at the end to study the zeros of the cell functions inside the critical strip. And in complex analysis, as you know, the zeros are related to the size of the function. So if you want to study the zero, you can as well study the size of the function. To study the size of the function, it makes sense to define a scale, because with respect to what? If you want to bound this L function, you bound it with respect to what? And that is called the analytic conductor, which is basically the measure of complexity of the L function. Okay, so the analytic conductor has this definition, which takes into account whatever parameters that appear in the functional equation. So there is an integer which appears in this functional equation that is taken into account. And then there are, in LS pi infinity, which are product of gamma factors, there are shifts by these numbers mu I. And these are the spectral parameters. Those are also taken into account. And finally, you take into account where S here is half plus IT. If you take a half plus IT, then this T is also taken. So there are three things that are taken into account in the definition of conductor. This is Q pi is an integer. It's called the level of the form. Mu i's are called the spectral parameters. And T is the location parameter, basically, for the L function. And together, this is called the conductor. So there are three aspects, three different flavors going into the definition of conductor. And you really want to measure the L function with respect to the conductor. So this one grows if Q pi goes to infinity, or if T goes to infinity, or if mu i's go to infinity. Okay, and when this is growing, how fast is the L function growing with respect to the conductor? So that's the main problem, right? Okay, so now, as I said, that there are different sources of L functions. So there is a, till now we have been looking at the automorphic form source, but there are also motivic L functions, which are sometimes geometric or coming from Galois representation type of thing. Okay, so here you start with an elliptic curve. So y square equals to x cubed plus x plus b. Okay, and for each prime, you look at this equation modulo that prime, and you count the number of solutions. That's basically given by this. So this number of points on this elliptic curve modulo p. Okay, and you expect that this is be almost like 1 plus p, because 1 plus p is the number of points lying on a straight line modulo p. And when you look at the elliptic curve, so this is the deviation from how many, from a straight line. And that is, this deviation is measured by this number called AP. And so you expect that there will be some fluctuation as you run over the prime p. AP will be positive, negative, growing, so on. And using these numbers, you can define an L function. Okay, so you form a Euler product. And here again, you have to normalize because these APs are known to be of psi square root of p. That's a theorem of Hasse. So you divide by square root of p, divide by p to the power s plus 1 by p to the power 2s inverse. And you look at this Euler product. This is easy to show that this is absolutely converging for sigma greater than 1 in that half plane. But analytic continuation of this is quite difficult, and even showing functionally, it was conjectured by Hasse and Well that it has analytic continuation and functional equation. And then Taniyama Shimura came along, and they even conjectured something stronger than that. They conjectured that this actually corresponds to a modular form. So there is a modular form whose L function matches with this. Okay, so that's the Taniyama Shimura conjecture. So I'll come back to that a little later. And there is another fantastic conjecture, which is more like a local global principle for elliptic curves, which says that the rank, if you look at the model Euler group EQ, and you know there is a torsion part and there is a free part, and the free part is given is determined by the rank of the free part. Then the rank of the free part of the model Euler group is same as the order of vanishing of this L function at the center, 1/2. Okay, so if you are coming from an elliptic curve background, then your point is will be this point will be 1. Your center will be at 1. But since I'm coming from an analytic number theoretic background, my center is always 1/2. All right. Okay. So now, so how are these elliptic curve L functions important? How are these related to the arithmetic problem? So, like Fermat's last theorem, for example, you know, if the last bit at least can be shown to be equivalent, showing that this type of, so you take the elliptic curve and twist by chi. So here chi is a Dirichlet character, and twisting by chi means looking at this Euler product. So you have AP by p to the power half plus s and 1 by p to the power 2s, but now you twist by chi p and chi p square. Okay. And if you are able to show that all these Euler products have analytic continuation and functional equation, which is actually analytic properties of this L function, if you're able to prove those analytic properties of this L function, then you'll be able to prove Fermat's last theorem. And as you know, that history goes, Wiles actually proved that this actually corresponds, this elliptic curve L function corresponds to a modular form L function. And so in one stroke, he got analytic continuation functional equation of all of them. Okay, so that's one application of analytic theory of L function to arithmetic. And here is another one. If you're interested in congruent number problems, so what is the congruent number? So, so an integer is called a congruent number if it is an area of a right-angled triangle with rational sides. Okay, for example, 6 is a congruent number. It's very easy to see because if you look at the triangle with sides 3, 4, 5, so it will be a right-angled triangle. Its area is 6. Okay, and it's quite difficult to show that 5 is also a congruent number because you will not find any integer-sided right-angled triangle for which 5 is an area. But there is a rational, okay, because you're only interested in rational sides, not integer. Okay, so you can show it's quite easy that, yeah, so what you're looking here is you want to get ABC rational numbers such that a square plus b square equals to c square, so that they form a right angle triangle. And the area, which is AB by 2, is n. Okay, and finding rational numbers like this is same thing as finding triplets. Okay, so finding so finding such a triplet is same thing as saying that this elliptic curve, which is y square equals to x cubed minus n square x, has a rational point, which is with y not equal to 0, right? So so having this triplet is same thing as saying that this elliptic curve has a rational solution. And as I mentioned in Bart's-Newton and Dyer conjecture, and you can show that this actually, if y is not equal to 0, then it cannot be a torsion point on here. So just excuse me. Sorry about that. So so as I was saying that if you look at y square equals to x cubed minus n square x, okay, so this has, and if you look at y not equal to 0, then that cannot be a torsion point in this elliptic curve. And so, and if you go back to the Bart's-Newton and Dyer conjecture, it said that the rank of the free part is same as the order of vanishing. So it was relating the rank with the analytic property of the L function. And so you can show that since it's not a torsion point, it has to be in the free part. So the free part must have some rank. And so saying that n is a congruent number is same thing as saying that the corresponding L function corresponding to this elliptic curve is vanishing at the center point. Okay, so this is another application of analytic theory. All right. So as I said, that you can also get L function from Galois representation like this. So this was started by Artin, and here it involves the Frobenius operator. So you're basically looking at the finite extension of Q, which is the number filled, and you take a Galois group and take a representation of the Galois group with a finite dimensional vector space V. And then using that, you can cook up an L function, which is defined by in this way. It's defined by Artin. And then Artin conjectured that if this representation is non-trivial and irreducible, then this L function is entire. Okay, and so that's also an analytic property of L function, right? As showing that this is an entire function. And this, if you take, for example, the dimension of B to be 2, okay, then you know that the representation either has to be like a cyclic or dihedral, tetrahedral, octahedral, or icosahedral. Except for icosahedral, we know that in conjecture for all of them. And whilst in his proof actually used that it's tetrahedral and octahedral two-dimensional representations are modular. Okay. Okay, so here are the main conjectures that you are interested in when you're looking at L functions. The first thing is, as Langlands said, that all L functions are automorphic. Okay, so not making it precise, basically it means like the Artin L functions are automorphic, the elliptic curve L functions are automorphic, and so on. And then there's this class of Bart's-Newton conjecture, which relates the rank of the elliptic curve with the order of vanishing of the elliptic curve. Okay, of course, then there's the grand Riemann hypothesis, which says the non-trivial zeros of the L function should be on the central line and not outside them. Okay, and then a big consequence of the grand Riemann hypothesis is the generalized Lindelof hypothesis, which says that the L function cannot grow too fast. Okay, so the size of the L function is bounded by the conductor raised to the power epsilon for any epsilon positive. So you can take epsilon to be very, very small, but still the L function cannot be larger than the conductor raised to that epsilon. Okay, so so we'll be now focusing mostly on the last problem, which is the Lindelof hypothesis. Okay, so if you look at the L function, and if you look at the basic properties of the L function, so you have this functional equation, And using the functional equation and the convexity principle from complex analysis, you can actually show that the L function is bounded by the conductor raised to the power 1/4. Okay, so the Lindelof says that you can drop this 1/4 altogether, and it will be bounded by the conductor to the power epsilon. But in the subconvexity problem, what we want to do is we want to just reduce the exponent from 1/4 by a little bit. Okay, it doesn't matter how little you decrease it by, but it still will have some consequence, as we'll see. For example, if you are interested in Hilbert's 11th problem, okay, so where you are interested in finding out the integers which can be represented by an n-array quadratic form over a number field, okay, then in most cases you can apply what's called Ziegel's mass formula, okay, except in one case where it does not work, where the quadratic form is positive definite ternary, okay. And you can show that here the problem is actually related to the subconvexity problem of certain L function. Okay? And this L function is basically the modular form L function that I mentioned. Okay, so you have to, so it's basically a fixed modular form L function twisted by Dirichlet character, and you want to get the subconvexity with respect to the modulus of the Dirichlet character. It's simpler than getting subconvexity in the level aspect. Okay, and this was proved by Duke and Schulz-Pellow in 1990 for the field of rational numbers, and in general by Koch-Delpy, Shapiro, and Sarnak. Okay, and this also gives you a solution to Linux problem about equidistribution of rational points on sphere and ellipsoid. Okay, but I'll not go into that time. And here's another application. So if you're interested in quantum chaos, so if you take x01, this is the Riemann sphere, and you take any modular form of weight k, level 1, then you can associate this measure on the modular curve, x01, and then you are interested to find out what happens to this measure as the weight k tends to infinity. So, and if the conjecture says that it converges weakly to this nice measure, okay, and this is called the quantum unique ergodicity. This is known, at least the limit is known to be this, but what we don't know is how fast is this this converge to this limit. So that is known, that will follow if you get some subconvex bound for this kind of functions in white house. Okay, so till now we know a lot about subconvex bounds. It's really a classical problem dates back to 1920 when Weil, Hardy, and Littlewood proved the first subconvex bound for the Riemann-Zeta function. T to the power 1/6, T to the power 1/4 was the convexity. And in the last 100 years, this has been improved a little bit, 1/6 minus 1/8 by 84. It's not that we didn't try, we really tried hard, but it's quite difficult to go beyond 1/6. Okay, so, breaking 1/6 is called breaking the Weil barrier, and it has turned out to be quite difficult. So here's another example. Burgess proved, so if chi is modulo b, that this is bounded by b to the power 3/16, 1/4 is the trivial bound. And this stood as a record for 60 years till recently in 2020, Pietro and Young proved that it can be reduced to 1/6. Okay, for degree 2, there's a sequence of papers. So first it started with Anton Good's paper, where he did the T aspect, and then there was sequence of papers by Ivanich with Friedlander and Duke between 1990 and 2010, where they settle all aspects of degree 2 L function. Okay, and the similar techniques also work when you go to higher degree L functions, but of special nature. For example, if you look at Rankin-Selberg convolution of 2 GL2 cross GL2 L function. Okay, the method they use there, it's the classical method, is the moment method. What you do is you want to study the size of one particular L function. Then you get hold of the family which contains this form in it. And then you estimate the L2 norm in that family. Okay. And then you once you have a bound for this L2 norm, by positivity, you can just drop all the other terms and you get the bound for an individual term. So the thing is that when you have, so when you're averaging over a family, you can expect to have a better understanding. Okay, so but your family cannot be too big because then it will wash out the contribution of one form. So there you have to balance the family. So you have to really find a right family containing the form, okay, which often turns out to be difficult. And in some cases, your family is just at the boundary. It's not really big enough, and also it's not. It's also not. So then you introduce what's called an amplification. Okay, so but we don't have any time to go into that. So there is another approach. It's called the period approach, and here you write down the L function as a period integral. Yeah, it's an orbital integral over here of the form. So pi is an automorphic form, and this is a vector in that form, automorphic representation. And then you use the theory of automorphic forms. This is a more geometric and representation theoretic approach, but it works remarkably in a very general scenario for GL2 and GL2 cross GL2, or even GL2 cross GL2, GL cross GL2 forms. Okay, and so I came up with a slightly different approach for subconvexity, and this is my approach. So if you have two automorphic forms, and suppose you write down the L functions as Dirichlet series in a classical way, then the Lindelof hypothesis basically says that if you look at the correlation of the coefficients that appear in the Dirichlet series, then there will be a lot of cancellation. It will be as small as root n, okay, where n will be the trivial one. Okay, so the Lindelof says that these sequences are orthogonal to each other, and that's what you want to prove. And from Rankin-Selberg theory, you can actually prove that if your length is very large, if it's larger than the conductor, then you have such a square root cancellation. But for subconvexity, you need to get cancellation when the length is like square root of the conductor. Okay. All right. Okay, so in this approach, what you do is you start with a very silly step. You separate the n from lambda 1 from lambda 2 just by introducing a Kronecker delta symbol. So delta nm equals to 1 when n equals to m and 0 otherwise. And then you replace in place of delta nm by an expansion, like a Fourier expansion that we have over here. And once you have, if you plug this in over here, the oscillation of lambda 1 and lambda 2 gets separated. And then you just, then you can do a lot of analytic number theoretic tricks after that, like applying functional, like summation formula, Cauchy-Schwarz inequality, reciprocity, all this type of things. Okay, and using that, I got a few interesting results. As the GL3 thing was, there were not many results about GL3. Actually, not a single result for genuine GL3 forms till 2015. And then I proved a few of them over here in the T aspect, in the twist aspect, and then I looked at GL2 cross GL3 in the T aspect. And then my students started looking at them, and they also did in the twist aspect, in the spectral aspect. Okay, and now there are quite a few people working on this, and they're also getting fantastic results. Okay, and this correlation thing is also related to other classical problems like the Dirichlet's divisor problem, the Gauss circle problem. And we hope that that same technique will also help in these problems as well. Okay, and here are some recent results. So this is during the lockdown period. Okay, so this is the first one is with my student and former postdoc, where we prove subconvexity for the GL3 cross GL2 L function in the level aspect. And this is with my former colleague and his student, J.K., and where we look at short sums and actually go beyond the Weil barrier. So this is quite interesting that in some cases we can go beyond Weil barrier. Anyway, so I think my time is up, so I'll stop with that. Thank you.
Thank you. Thank you, Ritabrata. Okay. It was a wonderful journey through L functions. A brief one though, but it gave a very good perspective. Can I just ask one question if it's allowed? I don't know whether we have the time. Did you mention that the estimate for pi x implies the Riemann hypothesis at some point?
Yeah. So if you have square root cancellation.
Okay.
Yeah. Then it will have Riemann hypothesis.
Good. So I guess we will have no time for any questions because it seems to be like back-to-back lectures. So
okay, so I'll stop sharing. Huh?
Thank you very much for your talk.
Thank you.
It was a wonderful experience. Mr. Gurmeet Singh, is it time for me to immediately start the next lecture, or is there a break?
No, sir. The time started now.
Okay.
Professor Sandeep.
Okay. So this is back-to-back lectures. So intense session from number theory to partial differential equations, quite a leap. So gives me great pleasure to introduce the second speaker today. This is Professor K. Sandeep from the Tata Institute. He has made significant contributions to a study of partial differential equations in hyperbolic space. He was awarded the Bhatnagar Prize in 2015 for his deep work. He discovered the hyperbolic symmetry of solutions in the Hardy-Sobolev-Mazia equations. It gives me great pleasure to have him speak here today, Professor K. Sandeep.
Okay, so let me share the screen first. Is it visible?
Yes, it's visible.
Okay, so first of all, thank you very much for the invitation and for your kind introduction. Okay. So I'm going to talk about partial differential equations and some inequalities. Okay. So if you have some experience with partial differential equations and you know that the inequalities play a very important role in the analysis of partial differential equations. Okay. So I'm going to talk about some inequalities which are related to some partial differential equations and which I have been working on and some of the related results. Okay. So before going directly into the topic, I will just motivate you through a somewhat a more elementary example. Okay. So I will start with a very elementary partial differential equations, what is known as the Dirichlet problem. Okay, I wanted to consider this problem. So let omega be a bounded open set in Rn with smooth boundary and consider the boundary value problem minus Laplacian of u is equal to f in omega and u is equal to g on boundary of omega. So omega is a given domain and f and g are given functions. So we want to find a function u which satisfies this relation. So this is the standard Dirichlet problem. So one learns a lot of methods to show the existence of solution for these kind of problems in any course on partial differential equations. However, I just want to recall one method which will help me to motivate the use of inequalities. Okay. So first note that if you are looking for a solution of this, that means first of all, I want Laplacian to be defined, Laplacian of u. That means better u be twice differentiable. And then it has to satisfy the boundary condition u is equal to g on the boundary. Okay. So first of all, I will start searching solutions in an admissible class of functions, which I will denote a is equal to set of all u element of C2 such that u is equal to g on boundary of omega. Okay. Now, so the solutions are going to be functions from this admissible class A, which satisfies the relation Laplacian minus Laplacian of u is equal to f. Okay. So now associated with this problem, you can also have an energy, which I will define like this for u in C2 of omega bar. E of u is equal to half of integral over omega modulus of gradient of u square dx minus integral over omega f into u dx. Okay. So whenever this Dirichlet problem represents some of the simplified models of some of the physical situations, this actually corresponds to the energy. Otherwise, in mathematics, you call such functions as energy functions. Okay, so these are the energy functions. And then the Dirichlet principle tells you the following. So it tells you that, so the given data, let f and g be continuous, that is the given functions. Then u0 element of A is a solution of 0, 1. That means u0 is a solution of this given PDE. If and only if E of u0 is equal to minimum of u in A, E of u. That means the solutions of the partial differential equations are nothing but the minimizers of this energy in this class of admissible functions. Okay, so you can see this as a mathematical statement of the least action principle, which tells you that the system tries to minimize its energy. Okay, so now if you are trying to find the existence of solution for the Dirichlet problem, that means this problem, using this theorem, then that means that we have to show that this minimum exists. That means there exists a u0 such that E of u0 is equal to minimum. Okay, so first note that this E, which is defined on this class A of functions. Okay, so E is defined from A to R, and you want to show that the minimum E attains its minimum on this class A. Okay, so one of the standard thing what we will do if we want to find a minimum is that we will try to show that the function E is bounded from below on this class A, and then try to take a minimizing sequence and try to show that the minimizing sequence converge. Okay, so now just look at this energy E of u, and first of all just try to let's see whether we can somehow show that this is bounded from below. So you can see that the first term is half of integral of gradient of u square, which is a non-negative term. And you have a second term, it is minus integral of f into u. Okay, so what can happen is that this quantity, integral of f into u, can goes to infinity as u varies. But there is a term which is here positive. So if we want E to be bounded from below, then there has to be some kind of cancellation or some kind of a balancing between these first and second terms. Or in other words, you should be able to somewhat estimate the second terms in terms of the first term. Okay, so let me just try to estimate the second term in terms of the first, and let me see what you are going to get. So this is what I already explained using the Dirichlet principle. If you want to show the existence of solution for the Dirichlet problem, then we have to show that the above minimizer exists. Okay, so let me try to estimate the second term, that you have integral of f into u, that you can just apply a Cauchy-Schwarz inequality. Then you can plug in some epsilon factor here and there, and then you can get an inequality like this. Okay, but the first term of the energy, if we have defined, that has term like integral of gradient of u square. Okay, however, here the second term I could estimate with something like integral of u square. Okay, but that doesn't help. U square and gradient of u square both are different. So if I can have an inequality like this, that is integral of omega u square is less than or equal to some constant times integral of gradient of u square for some positive constant c and for all u, then what will happen is that then I can plug this inequality back in the energy, and you can show that energy is going to be bounded from below by a constant which depends only on f. That way you can show that the energy is bounded from below, and then you can try to show that after that the minimum exists. Okay, but now the question is, can we have this kind of an inequality? That means integral of omega mod u square is less than or equal to a constant times integral of omega gradient of u square. So you can immediately see that it's not possible to have such inequalities in general. Okay, for example, for the simple reason is that you just put a constant, for example, u is equal to 1 or any constant, then the right hand side is 0, left hand side is not 0. Okay, so definitely you cannot have this kind of an inequalities because of the presence of constants. Okay, so what we want to see is that whether if constants are not there, can we have such inequalities, or is it possible to have such inequalities? First, let me demonstrate that such things are possible in one dimension. You can show that very easily such things are possible. Okay, so I'm going to start with an closed interval AB, and I'm going to take a function u which is C1 in the interval AB, which vanishes at the end A and B. Okay, so therefore the only constant function which satisfies this kind of condition is the zero function, which does not give any contradiction. Okay, then I can just integrate, I can take any x and then modulus of ux square. Ux, I can write it as integral from a to x u prime t dt, that is using the fundamental theorem of calculus. And then you can apply the Cauchy-Schwarz inequality and you can write it less than or equal to this. Okay. Now you can integrate over x and just divide by the constant, and you get an inequality like this. Integral of u square is less than or equal to integral from a to b modulus of u prime square. Okay, so that's the kind of inequality which I have been looking for here. Okay, in one dimension at least, it is possible under the assumption that the function vanishes at the endpoints on the boundary. Okay, so in fact, what I have proved here is a elementary or the simple version of the well-known inequality, what is known as the Poincare inequality. Okay, in fact, the more general form can be stated. Yeah. So this here itself, I showed that there exists a constant. With this constant, this inequality is true, but that doesn't mean that this is the best constant. So if you have, so you can find a best constant lambda 1. There exists an constant lambda 1 greater than 0, such that lambda 1 into integral a to b mod u square dt is less than or equal to integral from a to b modulus of u prime square dt. This relation holds for all u in C1 of AB with the u of A and u of B equal to 0. Okay, so this is the Poincare inequality in one dimension, and you can have a general version, the general form of this in the n-dimensional Euclidean space, which tells you that let omega be a bounded domain in Rn, then there exists an optimal constant lambda 1 greater than 0, such that lambda 1 of omega into integral over omega mod u square is less than or equal to integral over omega gradient of u square. This holds for all functions u, which is in CC1 of omega. That means C1 function with compact support in omega. Okay, so you can see that the constants won't appear here. The only constant appear is the zero function. So you can have this kind of an inequality, and that is the Poincare inequality. Poincare inequality, what we have been talking about. Okay, so I have chosen this this lambda 1 omega. That's the best constant in this inequality, and I chose that basically because it has some other significance. In fact, you can show that this lambda 1 is the first eigenvalue of the operator minus Laplacian in the appropriate function space. Okay, and yeah, so this inequality, we arrived at this inequality when we were trying to solve the Dirichlet problem. That is like minus Laplacian of u is equal to f into u. Okay, so if you are trying to solve more nonlinear problems, probably you will end up with this kind of an inequalities, but instead of this power 2, you may have other powers p or q or various other powers. Okay, and also we may have the question is, do we have inequalities in domains which are not bounded? For example, if you are dealing with partial differential equations in Rn and so on, then the question is, can we have such inequalities in the entire Euclidean space and so on? So now I'm asking this kind of general question. So the first thing I wanted to ask is whether this kind of an inequality, is it true can we have this inequality in Rn? Or in other words, does there exist a constant c greater than 0 such that c into integral over Rn, integral of mod u square is less than or equal to integral over Rn modulus of gradient of u square. This holds for all u in C1 of Rn, all C1 function with compact support in Rn. So unfortunately, the answer is no. You cannot, in the entire Rn, you cannot have. Okay. So that also essentially saying that in the language of spectral theory, the bottom of the spectrum of minus Laplacian in Rn is 0. Okay. So I will just briefly indicate why this is not possible. Before that, I will pose the question in a more general form, like what I described before. Instead of just asking this inequality with power 2, can you have with arbitrary powers p and q? Or in other words, more generally, can we have inequalities like this? Or does there exist a constant c greater than 0 such that integral over Rn mod u to the power q, then all to the power p by q, that is less than or equal to integral over Rn modulus of gradient of u to the power p for all u in CC1 of Rn. So can we have this kind of an inequality? Okay. So one may wonder, for example, why this kind of p by q and so on. And it is very easy to make out, because if you want this kind of an inequality holds for all u, then it should have the same the inequality should have the same homogeneity on both sides. Okay. Or in other words, if you replace u with some lambda times u, where lambda is a positive constant, then lambda to the power of lambda comes out on both sides has to be the same. Otherwise, you cannot have this kind of an inequality. Okay. So that's why here you can show that if you replace u with a lambda times u, lambda to the power p comes on the right, and the left-hand side also lambda to the power p comes out. So those kind of obvious obstructions are taken care with this kind of a normalizing in the power. Okay. So now the question is that can we have this kind of an inequality for some p and q? Again, there is another argument which is using scaling. You can show that, for example, if this inequality holds, there has to be a relation between p and q. Okay. And how we arrive at this is by using a scaling argument. That means if u is a C1 function with compact support, you can define another function by dilating the function u, in the sense that I can take a function, some u tilde of x is equal to u of lambda x. Then you plug that, again, you have to see what the power comes out, and they have to match. If you do such an argument, then you will immediately see that there has to be, if suppose we have such an inequality for p and q, then there has to be a relation between q and p, namely q has to be like np by n minus p. Okay, so that way you will immediately get that p has to be less than n, and then q has to be this relation. Okay, so if we need this kind of an inequality, that is not true for any q. Once you fix a p which is less than n, and then there will be a corresponding q which I denoted as p star. Okay, so the question is, the inequality is, it says that if there is an inequality, there is a relation between p and q. Now the next question is, do we really have such inequalities with this choice? The answer is yes. That is what is known as the well-known Sobolev inequalities. Okay, so let me just state what is known as the Sobolev inequality, which tells you that let 1 less than or equal to p strictly less than n, then there exists an optimal constant Spn which is greater than 0, such that Spn into integral over Rn mod u to the power p star all to the power p by p star is less than or equal to integral over Rn modulus of gradient of u to the power p dx. This holds for all u in C1 functions with compact support. Okay, so this inequality was initially established by Sobolev for p strictly greater than 1 and less than n. Of course, later on it was extended to the case of p is equal to 1 by Gagliardo and Nirenberg. And also the initial proof of Sobolev was using the singular integrals, and the proof of Gagliardo and Nirenberg was much simpler, just by using some clever integration by parts. Okay, so we know that this kind of an inequality holds, and so it basically tells you that given a p, you take the gradient of u to the power p, what power of u it controls. What it controls is mod u to the power p star norm, where p star is nothing but this quantity np by n minus p. Okay, So this is the sublow inequality what we have. And then what happens when p greater than in the complement of this range? What you can show is that when p is greater than n, the same gradient of u to the power p, what it controls is what is known as the Heller norm of the function. Okay, so this is what is known as the Morris inequality. Okay, so one case I have left out, p is equal to n, which I'll be talking about later. Okay, so first case is, so I'll be basically going to look at this inequality, sublow inequality for p less than n, and after that the case p is equal to n. Okay, so I'm not going to touch upon this inequality p is equal to n. So let me start looking at, so these inequalities, it may look at as if just an inequality, but this this best constant here in this inequality, the extremals of this inequality, they have all connection with various problems from PDE and geometry. Okay, so I'm going to explain some of the related problems first. And first, I'm going to talk about the sublow inequality in the case p is equal to 1. Okay, I'm going to, so let me rewrite that inequality for p is equal to 1. So first consider the case p is equal to 1. That is, we have this inequality. There is an optimal constant S1n, which is greater than 0, such that integral over Rn mod u to the power n by n minus 1 to the power n minus 1 by n, that is less than or equal to integral over Rn modulus of gradient of ux. This holds for all u in C1 functions with compact support. Okay, so this is the sublow inequality when p is on the right hand side, p is equal to 1, that is gradient of u to the power p equal to 1. Okay. So you can show that you can actually compute what is the exact value of this S1n. I will tell you this S1n, the value of S1n is n to the power 1 minus 1 by n into omega n minus 1 to the power 1 by n. Okay, where omega n minus 1 is the hn minus 1 measure of Sn minus 1. So Sn minus 1 is the unit sphere in Rn. So its surface is of n minus 1 dimensional. So hn minus 1 I means the n minus 1 dimensional area of the sphere in Rn. Okay, so that is my omega n minus 1. And so you can calculate this best constant, and this is this. Okay, and you can also show that equality is never achieved in this inequality. Okay, so that's about this inequality is n is equal to 1. So next, let me tell you that this problem is actually equivalent to a problem, to a very geometric problem, what is known as the isoperimetric problem. Okay, so let me explain what it is. So I'm sure many of us are familiar with the isoperimetric problem. So what it says is that determine the shape of the closed plane curve having a given length and enclosing the maximum area. Okay, so that means the length of a curve is fixed and it's a closed curve, and then you vary the shape so that it encloses the maximum area. Okay, so there is a rigorous form of this isoperimetric thing in the form of an inequality. Whatever I stated is in R2. You can even have it in any n-dimensional Euclidean space. So this is the isoperimetric inequality, the rigorous mathematical version of the isoperimetric inequality, which tells you that let omega be a bounded open set in Rn with smooth boundary. Okay, then you take the surface area of boundary. Okay, that is going to be greater than or equal to n to the power 1 minus 1 by n, omega n minus 1 to the power 1 by n into volume of omega to the power n by n minus 1. Or in other words, the volume it encloses. So this tells you that once the surface area is given or the boundary area is given and there is an upper bound on the volume it can enclose. Okay, and so this is a geometric problem. And not only that, we know that this constant is very sharp, and you will have equality when omega is a ball, the Euclidean ball. Okay, so you can observe that this constant n to the power 1 minus this constant, whatever I have talked about here, that's actually the same constant which has appeared in this inequality. Okay, so in fact, it was Federer and Fleming who proved that these two problems are equivalent. Okay, so they proved that the Sobolev inequality with P is equal to 1 is equivalent to the isoperimetric inequality. So one is an analytic inequality, other one is a geometric inequality. So the Federer and Fleming proved that these two things are equivalent. Or in other words, if you prove the Sobolev inequality, if you prove the Sobolev inequality, then if you prove the Sobolev inequality with the best constant, then that will immediately give you that the analytic inequality, so the geometric inequality. If you prove the geometric inequality, from there you can prove the analytic inequality. Okay, so the crucial tool used is what is known as the Poirier formula from the geometric measure theory. So this is the case of the inequality when P is equal to 1. So let me go to the, So let me just state another related problem in this case. For example, this kind of inequalities are also well studied in the case of Riemannian manifold. Okay, so let me talk about a case, what is known as the Cartan-Hadamard manifold. Okay, so Cartan-Hadamard manifolds. So these are the complete simply connected Riemannian manifolds of non-positive sectional curvature. And these manifolds, you have the Sobolev inequalities like in the Euclidean case. But finding the best constants, etc., it is not very obvious. So the Cartan-Hadamard conjecture, well-known Cartan-Hadamard conjecture, tells you that the same isoperimetric inequality holds in any Cartan-Hadamard manifold with the same Euclidean constant. Okay, so this is actually equivalent. You can also have the same kind of an inequality, analytic Sobolev inequality, and so the proving the conjecture is equivalent to finding the best constant in the Sobolev inequality or working in this form. Okay, so this is the Cartan. So this goes back to Weil in 1926. In the case of n is equal to 2, he uses tools from complex analysis. And later on in the 1960s or 70s, and the conjecture was formulated by many people like Gromov and Oban and various people, and that's what is today known as the Cartan-Hadamard conjecture. And so later on in 1984, Kroc proved this result in n is equal to 4. N is equal to 3, Kleiner proved the result in 1992. And n greater than or equal to 5, the conjecture is still open. Okay, so this is the case with n is equal to 1, some of the important problem. So now let me goes to the case P is equal to 2. Okay, so when P is equal to 2, this is how the inequality becomes. S2n, that is going to be equal to integral of mod u to the power 2n by n minus 2. This is less than or equal to this. Earlier, the last I was discussing the case here, instead of 2, it was 1. Next, let me take the case 2 is equal to 1. P is equal to 2. Okay, so this is the explicit form of the inequality, whatever I wrote for general P earlier, and which I am rewriting for P is equal to 2 here. Okay, so now this inequality has also a lot of implications, and it's also connected with various PDEs coming from differential geometry. Okay, so for this inequality, you can show that the extremal functions exist. Okay, and in fact, you can show that if you use an extremal of this inequality, then there will be an associated Euler-Lagrange equation, and it solves this kind of an equation, that is minus Laplacian of u is equal to u to the power n plus 2 by n minus 2, and u positive, and integral over Rn gradient of u square is finite. Okay, so you can show that if u is an extremal of this, then it solves this partial differential equation. So if you want to find an extremal of this inequality, that is equivalent to finding finding all solutions of this inequality, this partial differential equation. So these are very difficult problems in general, classifying all solutions of certain partial differential equation. But however, this partial differential equation has a lot of hidden structures. For example, it has rotational symmetry, it has conformal invariance, and there are various things. And using all these tools, in fact, one can indeed classify the solutions. Okay, so as I told, it is a rotational symmetry. You can show that if U is a solution, then U has to be radial with respect to some point. And there are various invariants like conformal invariants, in the sense that if K is a conformal map from Rn to Rn, then you suppose J of K denote the Jacobian of this conformal map. Then you define a function U tilde is equal to Jacobian to the power n minus 2 by 2 into U of Kx. Then this is also going to be a solution. So so exploiting these kind of hidden structures, there have been many proofs, and people have finally classified the solutions of this equation. And I will just state explicitly what are all solutions of this equation. Okay, so any extremal of this inequality, or equivalently, any solutions of this partial differential equation can be obtained basically of like this. It will look like this for some epsilon and for some x naught. Okay, so there have been many proofs of this, and there are some methods which are using geometric methods, and there are various other analytical tools. You can show that you can classify all the externals of this inequality. Okay. So this is also very closely, this inequality is also closely related to a geometric problem or a geometric result of beta, which tells you that let G be a metric on the unit sphere Sn, conformal to the standard metric on Sn, then G is of constant scalar curvature 1, if and only if G is of constant sectional curvature 1. Okay, so in fact, using stereographic projection, and you can actually show that the inequality, whatever I stated in Rn, is equivalent to this geometric theorem of beta, which tells you this result of conformal metric. Okay, and in fact, these problems, what is important is that this exponent n plus 2 by n minus 2. There is a whole class of partial differential equation which involves that kind of an exponent, and that creates a lot of difficulty for solving those kind of partial differential equations. One such well-known problem is what is known as the Yamabe problem from differential geometry. Okay, so the problem tells you that let Mg be a compact Riemannian manifold of dimension n, and let's denote its scalar curvature by Kg. So can we find a metric G tilde conformal to G such that G tilde has a constant scalar curvature? Okay. So what Yamabe did is Yamabe represented, so G tilde is a conformal metric, means it's a positive multiple of the original metric. Okay. So G tilde, you can write it as U to the power 4 by n minus 2 into G, where U is a positive function. Then the scalar curvatures of Kg, that is of the scalar curvature of G, and scalar curvatures of G tilde, that is Kg tilde, they are going to be related by this partial differential equation. Okay, so then the Yamabe problem reduces to solving whether you can solve this partial differential equation for a constant K. Okay, so that is the question, the Yamabe problem. So the geometric problem of Yamabe, which reduces to finding this kind of, solving this kind of a partial differential equation for a constant K. Okay, then that constant is going to be the curvature of the constant curvature of the conformal metric. Okay, so this problem, as I mentioned in the beginning, I showed that the Dirichlet problem can be solved using a minimization problem. Corresponding to this partial differential equation also, you can have a minimization problem. Then you can show that the quantity you are to minimize, that is bounded from below. Then the question is the minimizing sequence, whether it will converge or not. Okay, and in general, the minimizing sequence may not converge. Okay, in fact, in his first, when Yamabe published the paper first, he made a mistake and he assumed, he just took it as for granted that the minimizing sequence converges. And later on, it was pointed out by Trudinger that this is not the case in general. And later on, the proof was repaired with the effort of many people over a period of 2 decades. And finally, the final proof involves even what is known as the positive mass theorem and so on. So what I wanted to tell you is that in the solution of this problem, the extremals of this inequality, these functions which is the extremal of the Sobolev inequality, that play a very important role in the solution of this equation. So the Sobolev inequality when P is equal to 2 are closely related to this kind of a partial differential equations. And if you want to solve these kind of partial differential equations, it's important that you have that sharp inequalities, their extremals, and various other things. Okay, so this is the thing. So in general, so let me just go back and let me show. This was my Sobolev inequality. This is the inequality which I have. I discussed this case when P is equal to 1 and P is equal to 2. Okay. Now let me try to take the case P is equal to 1. Right now I don't have an inequality. So I have this inequality and this best constant is Pn. So and there are works which computed these constants. Okay. So that's what I'm going to mention next. Okay. Yeah. So this S in P, that the best constant can be computed explicitly, and this is an explicit expression, and it goes way back to various people, to Rodimich in 1966, Oban in 76, Talenti in 76, and so on. So what you can observe here is that as P goes to n, this constant goes to 0. So the inequality, you cannot take the limit as P goes to n in the inequality, and it becomes a trivial inequality. Okay, so now, so what you can do, so this is the inequality, and as P goes to n, this quantity goes to 0. Then if you take the limit, it becomes integral of gradient of u to the power n greater than or equal to 0. It's a very trivial information. There is nothing to obtain. And P star is in P by n minus P. This goes to infinity. So one may expect maybe whether L infinity norm can be controlled by Ln. Unfortunately, that's also not possible. So what happens is that you can try to see what exactly we can do. Okay. So to see what we can do in the case of P is equal to n, let me rewrite this inequality in a different form. Okay. This has the same homogeneity on both sides. So I'm going to write this inequality in an equivalent form. For example, I can assume that on the right-hand side is 1, gradient of u to the power p is 1. Then it says that this supremum is less than or equal to 1. Or equivalently, this inequality can be equivalently written like this. That means you take the integral over Rn mod u to the power p star, and you take the supremum over all C1 functions with compact support, and with the constraint gradient of u to the power p less than or equal to 1, then that is going to be bounded. Okay, and then this p star, as p goes to n, this goes to infinity. Okay, so you cannot really pass to the limit here as well. But in this form, the question what can I ask is, instead of a polynomial power mod u to the power p star, can we have something better? Yes, it is indeed true that the first result was obtained by people like Prodinger, and later on this result was further refined by Moser, and what we call today as the Moser-Prodinger inequality. Okay, so the inequality tells you that, for example, exactly like here, instead of mod u to the power p star, what I have obtained is, what they proved is that you can have an inequality like this. And you can, instead of polynomial power, you can have an exponential quantity. Or in other words, when p is equal to n, n is the dimension, what you can control is the exponential of u and some powers of u. That was, so this fact was first observed by many people, Pitre, Prodinger, and many other people. And finally, a sharp form of that was obtained by Moser in 1971. I will tell you what was his motivation to find such a thing. Okay, so the statement is, there exists a positive constant C0 depending only on the dimension n, such that supremum over u in CC1 of omega integral over omega gradient of u to the power n dx is less than or equal to, or e to the power alpha mod u to the power n by n minus 1 is less than or equal to this constant times measure of omega. Mod omega means the measure of omega. This holds for all alpha less than or equal to a constant alpha n, where alpha n is nothing but this constant, where omega n minus 1 is the surface measure of the n minus 1 dimensional ball in Rn. Okay, unit ball in Rn. Okay, so you can have an inequality with alpha. There is an optimal constant. What happens is that if this alpha is bigger than this alpha n, that's what I have written here. Moreover, if when alpha greater than alpha n, the above supremum is infinite. So that was the case, the Moser. So let me tell you what was the reason for Moser to prove such an inequality. So again, he was studying a problem of prescribing the Gaussian curvature on the two-dimensional sphere in a conformal way. Okay. So again, let me go to this problem from the Riemannian manifolds. Let Mg be a two-dimensional Riemannian manifold, and let G tilde be a metric which is conformal to G. So therefore, you can write G tilde is equal to some e to the power 2u into G. Then the Gaussian curvature of the two metrics, that is G and G tilde, which I denote respectively by Kg and Kg tilde, they are related by this kind of a relation, partial differential equation. Okay. So again, the question in conformal geometry is, can you classify all curvatures of conformal metrics? Okay. So Moser was studying this question in the case of sphere or S2, the two-dimensional sphere. Okay. So he was studying this in the case of two-dimensional sphere. In that case, for example, whatever theorem I proved here, stated here in a Euclidean space Rn, he proved the same kind of an inequality on the sphere S2. So the inequality says that, so S2 denotes a two-dimensional sphere. He proves there exists a constant c greater than 0 such that supremum over all functions u with this kind of constraint, and then e to the power 4 pi u square, this is less than or equal to c. Okay, so that is what Moser proved. And why he was in need of this result, that is because, and if you look at this kind of a partial differential equation on the case of sphere, and then solving that is associated to finding the minimum for a functional. Okay, that functional, again, you have to show that it is bounded from below. And for that, you need an inequality like this, which I have written below, okay, and which you can deduce from here. Okay, so with the help of this kind of an inequality, what he established, what Moser showed that this inequality, the functional which you want to find the minimum, that is bounded from below. And therefore, you can think about the minimum. Then you have to take a minimizing sequence and you have to show that it converges. Okay, but unfortunately, he could not do that, and he succeeded in a very limited case in the case of real projective space, or in other words, if you restrict to functions which are symmetric. Okay, so that is the only case which he succeeded here. And then he solved the problem partially. Of course, in the full generality, the problem was addressed later on. Okay, and you see, in the case of sphere, there are many other topological abstractions coming into picture. I'm not talking about any of these things. So I just wanted to mention that the Moser's idea was to use this kind of an inequality to solve this problem. Okay, so this kind of an inequality, so this inequality, this is the inequality Moser proved, and the last line which I wrote, and this he proved there exists a C, and a more optimal form of this inequality was obtained by Onofre, and he was studying something from string theory and that is where he has obtained this kind of an inequality. And later on, this type of inequality was generalized to Sn by Beckner, and there are various forms of this inequality, okay, and various generalizations. Okay, so there have been various developments, and so now the question is whether these kind of inequalities are true in other kind of manifolds. Okay, so I'm not going to the details. So me and Mancini, my collaborator, in 2010, we established that these type of inequalities are true in the two-dimensional hyperbolic space. Okay, so our things can be extended even to any n-dimensional hyperbolic space. Okay, and later on, some people in 2016, they extended our results in an appropriate form to any Cartan-Hadamard manifold. Okay, so I'm not going to the details due to the lack of time. And then there are higher dimensional versions of inequality, which involves the higher order gradients. You can define a higher order gradient like this, Laplacian to the power k by 2, if k is even, this kth order gradient. And for k odd, you take the gradient of the Laplacian to the power k minus 1 by 2. And then Adams proved an inequality like this, which looks very similar to the inequality which I stated for Moser. The statement looks very similar, but the approaches are different, very different. Of course, the paper is in Annals of Math, so you can see that there is a considerable difficulty in proving that. Okay, and it was using some tools from harmonic analysis. He proved that. And after that, there have been many attempts to establish such inequalities in manifolds, basically to solve various partial differential equations coming from geometry and so on. Okay, so this inequality was generalized to any compact Riemannian manifold by Fontana in the form whatever I mentioned. Then I took it up the case in the, then the question is, in the hyperbolic space, do we have such inequalities? Okay. So there was some preliminary work by some people. And then after that, there was an approach by me and one of my former student. And we tried to study this in the case of another problem which is coming from conformal geometry. And there is, since I don't have much time to explain, so I will just tell that, like the case of prescribing the Gaussian curvature, there's a question of prescribing the higher order curvature, what is known as the Q curvature. I'm skipping all these slides. And in that case, you will end up with this kind of a partial differential equation. Okay. And then the question is, if you talk about prescribing this kind of curvatures, you need to prove inequalities which involves these geometric quantities. We did succeed, and there are some technical details. And then, so we managed to prove that, so you take the n-dimensional hyperbolic space, you have an inequality like this. And using this inequality, we could prove some result which prove the existence of solution for this kind of equations, which I stated, which prescribe the Q curvature equation. We could get some preliminary results. So we pushed it further, and recently we obtained another result in a general Hadamard manifolds. So there's a result, joint work with one of my collaborators, Jerome Bertrand. So MGB an n-dimensional Hadamard manifold with a sectional curvature bounded from below by a negative constant and Ricci bounded from below by a negative constant, then you can have this kind of inequality. Of course, we have some consequences of this, and you can have some application to solvability of the equation. Okay, so I will stop here, and thank you very much.
Thank you very much, Sandeep, for a wide introduction, or at least a view of the grand questions in partial differential equations. It was a pleasure listening to you. Okay, so we don't have any time. I must thank both speakers, Professor Sandeep from TIFR and Ritabrata Munshi for an excellent afternoon session. Thank you very much.
Thank you.
Sir, may I stop the live streaming?
Yes, please. Yes, please.